Hi, welcome to the COMSI 137 lecture. Sunny here. In this module, we will discuss analog transmission. Let's start. If digital transmission is desirable, why do we need analog transmission? Unfortunately, available channel bandwidth is scarce, hence we are forced to use a bandpass channel. Traditionally, converting digital data to a bandpass analog signal is called digital to analog conversion. Likewise, converting a low-pass analog signal to a bandpass analog signal is called analog to analog conversion. Digital to analog conversion is the changing of characteristics of an analog signal based on the information in digital data. But first, we define some terms. Bit rate is the number of bits per second. Baud rate is the number of signal elements per second. In analog transmission of digital data, the baud rate is less than or equal to the bit rate. A carrier signal or carrier frequency is a high-frequency signal that acts as a base for the information signal that is produced by the sending device in analog transmission. Modulation or shift keying is the modifying the characteristics of a carrier frequency to send data. There are four types of digital to analog conversion: amplitude shift keying or ASK, frequency shift keying or FSK, phase shift keying or PSK, and quadrature amplitude modulation or QAM. In ASK, the amplitude of the carrier signal is varied to create signal elements. Both frequency and phase remain constant, while amplitude changes. An example is the binary ASK. This is the original signal, and this is the carrier frequency. As you can see, if the value is 1, the modulated signal took the shape of the carrier signal. But if the value is 0, the level is 0. In FSK, the frequency of the carrier signal is varied to represent data. Both peak amplitude and phase remain constant for all signal elements. An example is the BFSK. Again, this is the original signal and this is the carrier frequency. As you can see, when the value is 1, the frequency is increased. But if the value is 0, it took the shape of the carrier frequency. In PSK, the phase of the carrier is varied to represent two or more different signal elements. Both peak amplitude and frequency remain constant. An example is the BPSK. Again, this is the original signal and this is the carrier signal. If the value is 1, it has the same phase as the carrier signal. But if the value is 0, it shifted.
The simplicity of BPSK enticed designers to use 2 bits at a time in each signal element, thereby decreasing the baud rate and eventually the required bandwidth. The scheme is called quadrature PSK or QPSK because it uses two separate BPSK modulations. One is in phase, the other quadrature or out of phase. The incoming bits are first passed on serial to parallel conversion that sends one bit to one modulator, the next bit to the other modulator. This example, the in-phase carrier is in 0 degrees. Quadrature carrier is in 90 degrees.
A constellation diagram helps to define the amplitude and phase of a signal element when we are using two carriers, one in quadrature of the other. It is useful for dealing with multi-level ASK, PSK, or QAM. The x-axis represents the in-phase carrier and the y-axis represents the quadrature carrier. A signal element is represented by a dot. The bit or combination of bits it can carry is often written next to it. Here is a concept of a constellation diagram. The diagram has two axes. The horizontal x-axis is related to the in-phase carrier. The vertical y-axis is related to the quadrature carrier. For each point on the diagram, 4 pieces of information can be deduced. The projection of the point on the x-axis defines the peak amplitude of the in-phase component. The projection of the point on the y-axis defines the peak amplitude of the quadrature component. The length of the line that connects the point to the origin is the peak amplitude of the signal element. The angle the line makes with the x-axis is the phase of the signal element. Here is a PSK constellation diagram. The bit 0 with a 0 degree phase is represented here. The bit 1 with a 180 degrees phase is represented here. Here is a 4 PSK with a bit rate of 10 and a baud rate of 5. The bits 00 has a phase of 0 degrees. The bits 01 has a 90 degrees phase. The bits 10 has a 180 degrees phase. The bits 11 has a 270 degrees phase. Here are the values of the signal presented in the table. Here is its representation in a constellation diagram. Here is an 8 PSK constellation diagram. PSK is limited by the ability of the equipment to distinguish small differences in phase. This factor limits its potential bitrate. So far, we have been altering only one of the three characteristics of a sine wave at a time. But what if we alter two? Why not combine ASK and PSK? The idea of using two carriers, one in phase and the other quadrature, with different amplitude levels for each carrier is the concept behind the quadrature amplitude modulation. The possible variations of QAM are numerous. Here is an 8 QAM signal. As you can see here, it has two amplitudes and four phases. This is the same signal represented in a constellation diagram. Analog to analog conversion or analog modulation is the representation of analog information by an analog signal. One may ask, why we need to modulate an analog signal? It is already analog. Modulation is needed if the medium is bandpass in nature, or if only a bandpass channel is available to us. An example is radio. The government assigns a narrow bandwidth to each radio station. The analog signal produced by each station is a low-pass signal, all in the same range. To be able to listen to different stations, the low-pass signals need to be shifted, each to a different range. Analog to analog conversion can be accomplished in three ways: amplitude modulation or AM, frequency modulation or FM, and phase modulation or PM. FM and PM are usually categorized together. In amplitude modulation, the carrier signal is modulated so that its amplitude varies with the changing amplitudes of the modulating signal. The modulating signal is the envelope of the carrier. In frequency modulation, the frequency of the carrier signal is modulated to follow the changing voltage level of the modulating signal. As you can see, in the modulating signal, the part with the higher amplitude has a higher frequency in the FM signal. In phase modulation, the phase of the carrier signal is modulated to follow the changing voltage level of the modulating signal. In FM, the instantaneous change in the carrier frequency is proportional to the amplitude of the modulating signal. In PM, the instantaneous change in the carrier frequency is proportional to the derivative of the amplitude of the modulating signal. PM is used in mobile communication systems, while FM is mainly used in FM broadcasting. This ends Module 8. Thank you.